In this lecture, is a subject is DSD, Digital System Design, and topic is Combinational Circuit Design design, right? So in this video lecture, we'll design a half subtractor, full subtractor, and code conversion, code converter circuit. So in this video lecture, we'll design a half subtractor combinational circuit, full subtractor combinational circuit, and the code converter circuit. Right? Let us start with the half subtractor. Half subtractor. What is definition of half subtractor? It is a subtraction of one bit minus another bit. It is called a half subtractor. So it is a minus b is called a half subtractor. So it's have the two input variable, and let's see how many output variable requires. So in the half subtractor, if you subtract one bit minus another bit, it's have the difference and the borrow bit. Difference and the borrow bit. Right? So it required the two output variable. One is the difference and another is the borrow. So any half adder, half subtractor, it's have a two input variable A and B, and it produces the two output variable difference and the borrow bit. Difference and the borrow bit. So we have identified how many input variables required, output variables required. We have assigned the symbols A, B and D and B. Next step is to prepare the truth table. Right? Let's prepare the truth table of half subtractor. So it's have the two input bit and it's have the two output bits difference and borrow. So all the possible combination of input and its output according the definitions. So here our problem statement is A minus B, right? So let's check for the first combination. If we subtract 0 minus 0, what is the difference bit? It is 0. And what is the borrow bit? It is also 0. So difference bit is 0 and borrow bit is also 0. If you want to subtract A is equal to 0 and B is equal to 1, 0 minus 1, then we need to take one borrow, right? So it is a binary subtraction, so borrow value is at 2. Borrow value is 2, right? So its borrow is equal to 1. We taken a borrow and the difference output is 2 minus 1, it is 1. So difference bit is 1. So when we subtract the 0 minus 1, difference bit is 1 and borrow bit is also 1. Now for the third input combinations, when A is equal to 1 and B is equal to 0, so it is 1 minus 0. So 1 minus 0, difference is 1 and borrow bit is equal to 0. So difference bit is equal to 1 and borrow bit is equal to 0. Now for the fourth combination, 1 minus 1. So when we do the 1 minus 1, then difference between 0 and borrow bits is also 0. The difference is 0 and borrow is also is equal to 0. So this is the truth table of an half adder as per the problem step. Next step is, after preparing the truth table, next step is we have to prepare its we have to minimize each output variable. So here the input have the two inputs. So to Carnot map, it is a two variable Carnot map, right? So for the D function, let's say A bar A, B bar and B. Let map from the two table to Karnaugh map. So in a min term 0, it's have the D difference bit is 0. For the min term 1, difference bit is 1. And for the min term 2, difference bit is 1. And for the min term 3, difference bit is 0. Right? Let me make the group of 1. So for this group, for this one, group of 4 is not possible. Group of 2 is also not possible. So it is a group of 1. Similarly, for this one, group of 4 is not possible, group of 2 is also not possible, so make the group of 1. So the minimize the equation of difference bit is A bar into B, common variable in first group, plus common variable in the second group. It is A into B bar. So this is nothing but the A XORing B. This is for the difference bit. Similarly, we have to prepare for the borrow bit. Okay. So here the A bar, row B, B bar column and B. So in a different borrows bit, and in min term 0, borrow is equal to 0. So here it is in 0. For the min term 1, borrow is equal to 1. So here in min term 1, borrow is equal to 1. And for the min term 2 and 3, borrow bit is equal to 0. So it's have a 1 ones and rest of are 0. So group of ones and the borrow bit, it's have the A bar into B. So this is logic of the borrow and this is logic of the difference. Right? It can implement using the logic diagram. Difference, it is an XORing of A and B. It is a difference bit, and borrow, it is an A and B. So for the borrow, A is a complements A bar and B, it is for the borrow bit. So this is the implementation of a half subtractor using two input XOR, one NOT gate and the one AND gate. So here it is an A bar into B and this is the XORing of A and B. XORing of A and B. Our next combinational circuit, it is an full subtractor. Full subtractor. Full subtractor. So in a full subtractor, it is 2-bit subtraction with the previous stage borrow. So it is called a 3-bit subtraction. So here we want to subtract x minus y minus z. And it produces the 2 bits. One is the difference bit and one is the borrow bit. One is the difference bit and another is the borrow bit. Right? So here we want to perform x minus y minus z and produce the z and the b, difference and the borrow. So it's have the 3 input variable and the 2 output variable. So for the 3 input variable, let's prepare the two table of 3 input variable. So for the 3 input variable, let's have the 8 possible combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Right? For each input combination, let's find the what is the difference bit and what is the borrow bit. Right? So here we remember what the function we want to perform. We want to perform x minus y minus z. Right? So let me subtract for the first input combination 0 minus 0. It is 0 and the answer minus 0. So it is 0, difference is 0 and borrow is also 0. Now for the 0 minus 0, so the difference is 0 and borrow is also 0, and 0 minus 1, it produce the difference is equal to 1 and borrow is also is equal to 1. 0 minus 1. So if we do the 0 minus 1, if the difference is 1 and borrow is also 1, we need to take the borrow, because 0 minus 1 is not possible. We need to take the borrow from the uh, that higher digits, right? So difference and borrow bits, both the bits are 1 and 1. Now for the 0 minus 1, difference and borrow bits, both the bit are 1 1. Minus 0, so it is as it is, means the difference bit is 1 and borrow bit is also 1. 0 minus 1, difference bit is 1 and borrow bit is 1, and again minus 1, so difference bit is 0, but if the borrow bit is equal to 1. 1 minus 0, difference bit is 1 and borrow bit is equal to 0, and 1 minus 0, so difference between bit is 1 and borrow bit is 0. 1 minus 0, difference bit is 1, borrow bit is 0, and again minus 1, so difference bit is also 0 and borrow bit is also 0. 1 minus 1, it is both the bit are 0 0 minus 0, so again 0 0. 1 minus 1, so both the bits are 0 0 minus 1, so it is 0 minus 1. For the 0 minus 1, difference bit is 1 and the borrow bit is also equal to 1. So this is truth table of the full subtractor. Next step is to find out the minimize the each output variable using the Karnaugh map. So here it is a 3 variable truth table. So we require the 3 variable Karnaugh map. So let me prepare the 3 variable Karnaugh. 3 variable Karnaugh. Here it is an a bar, x bar, and x, y bar, z bar, y bar, z, y z, and y z bar. Right? Now mapping. So in a zeroth min term, difference bit is 0, and for the 1 min term, difference bit is 1, and for the 2, difference bit is 1, and for the third min term, difference bit is 0, and for the fourth min term, difference bit is 1, and for the fifth, difference bit is 0, and for the sixth, difference bit is 0, and for the seventh min term, difference bit is 1. Right? So it is similar to the full adder sum bit. So difference logic will get here it is a group of 1, this is also group of 1, this is also group of 1, this is also group of 1. So it's have the 4 group and each group size is 1. So here the common variable are x bar, y bar and z, x bar, y bar and z. From the second common variable are x bar, y and z bar. From the third common variable are x, y bar and z bar, and from the fourth common variable are x, y and z. Okay. Let's take the x bar common from the first two terms, so it is z, y bar z and y z bar. From the second two term, let's take the x common, so it is a y bar z bar plus y z. Right. So x bar, and this is nothing but the x, y and z XORing plus y. This is nothing but the y and z XNOR. Right? And we know XNOR, it is an invert of XOR. So this XNOR, this x, so this XNOR, it is an invert of XOR. Let's take the this y x or z is equal to some variable, let's say it is an a, so here x a into x a, so this is nothing but the x and a are in XORing, right? So substitute the value of x, so it is an, so difference bit is XORing of x, y and z. All the 3 bit, if we do the XOR, it produce the different bits of an full subtractor. Let's similarly derive for the carry bit. Okay. So let me prepare for the carry bit, different borrow bit. here it is an x bar x, y bar z bar, y bar z, y z, and y z. So let me map from the two table to the Karnaugh maps. So for the min term 0, different borrow bit is 0. For the min term 1, borrow bit is equal to 1. For the min term 2, borrow bit is equal to 1. For the min term 3, borrow bit is equal to 1. For min term 4, borrow bit is equal to 0. For min term 5, borrow bit is equal to 0. Min term 6, borrow bit is equal to 0. And min term 7, borrow bit is equal to 1. Let me prepare the group. So group of 8 is not possible, group of 4 is also not possible, but the group of 2 is possible. So let's prepare the group of 2. Similarly, for this one is also group of 2 is possible, for this one group of 2 is possible. So borrow bits have the 3 group, and each group have the group of 2. So for first group, for this group, common variable are x bar and z. From the second group, common variable are x bar and y. And from this third group, common variable are y and z. Y and z. Right? So this is the logic of the borrows bit of a full subtractor. It is a x bar into z plus x bar into y plus y into z. Right? Let implement it. The implementation of full adder using different logic gates or x and y, we do the XORing, and it is XORing with z. It is produce the difference. And for the sum bit, here it is x and y ending, y and z ending, and x bar and z ending. This is the borrows bit, right? Also, we can implement uh, full subtractor using the full adder. Just the difference between the full adder and full subtractor is required one extra NOT gate. So if we NOT of x and produce the full from the full adder, that can convert it into the full subtractor, right? So this is the logic to implementation of an full subtractor. Also, we can implement the full subtractor using the half subtractor. Is we can use one half subtractor which have the two bits, let's say x and y, and it produce the difference and the borrow. The difference is again the subtractor using the another half subtractor, and it produce the final difference and borrow from the second one, and the borrow of the both 1 and 2 will do the ORing, will produce the final borrow of the design. So using the half subtractor also we can implement the full subtractor. So this is also we can implement a full subtractor using the two half subtractor and the OR gate. Two half subtractor and the OR gate. Right? So it is an implementation. If you want to check how it implement this using the two half subtractor and the OR gate, then it can be easily we can be through it, right? So this is the full subtractor using the two half subtractor and the OR gate diagram. Now let's see next our design. It is a code converter. Let me design one more combinational circuit. It is a code converter circuit. Code converter. So in this code converter, Let's design here a BCD to access 3 code convert. BCD to access 3 code convert. So we know in a BCD number of input variable are 4 binary coded decimal. So to code the binary coded decimal 0 to 9 we require at least 4 variable, and let me give this name of variable is D3, D2, D1 and D0, and we want to convert into the access 3. So let me give the output of access 3 variable name x3, x2, x1 and x0. Right? We know the logic how to convert the BCD to access 3. So access 3 it is an addition of 3. Whatever the BCD number we have to add the 3. It is a access 3 of the any BCD number. So in BCD it's have a 0 to 9. So 0 to 9 in a binary it is 0 0 0 0 0 1 0 1 0 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 8 in 9 can represent 1 0 0 1. Okay? So this is the BCD number 0 to 9. Now if we add the 3 which produce the access 3. So 0 0 0 means zeros decimal. This is 0 1 2 3 4 5 6 7 8 and 9. So for the 0 if we add the 3 it is a 3. So whatever the binary of the 3 it is access code of BCD 0. For the BCD 1, 1 plus 3 is 4. So whatever the binary code of 4, it is an access 3 of code for the 1. Right? Similarly, if it 2 plus 3, it is 5. So 5 can be coded in binary 0, 1, 0, 1. 3 plus 3 is 6, and 6 can code is 0, 1, 1, 0. For the 7, it is an 0, 1, 1, 1. For the 8, 5 plus 3, it is 8. 8 can write in binary is 1, 0, 0, 0. And 6 plus 3, it is a 9. And the 9 can write in binary is an 1, 0, 0, 1. And 7 plus 3 is 10. And 10 can write in binary is 1, 0, 1, 0. 8 plus 3 it is an 11, and 11 can write in binary is 1 0 1 1, and 9 plus 3 it is equal to 12, and 12 can write in a binary is 1 1 0 0. Right? So this is the truth table of BCD to access 3 code converter. Now our next step is to minimize the each output variable using the Karnaugh map. So here there are 4 input variables. So the Karnaugh map size is a 4 variable Karnaugh map. So let me first prepare the Karnaugh map of X3. Right? MSB bit, and it is a 4 variable Karnaugh map. So here 2 MSB bit B3 and B2. So B3 B2 bar, B3 bar, B2, B3 B2, B3 B2 bar. Here are the 2 LSB bits. So B1 bar, B0 bar, B1 bar, B0, B1 B0, and B1 B0 bar. So here it is min term 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 and 15. Right? Now let me map the x3. So for the min term 0, 0, 0, 0, 0, output x is equal to 0. For min term 1, x is equal to 0. For min term 2, x is equal to 0. For min term 3, x3 is equal to 0. For min term 5, min term 4, x3 is equal to 0. For min term 5, x3 is equal to 1. For min term 6, x3 is equal to 1. For min term 7, x3 is equal to 1. For min term 8, x3 is equal to 1. And for the min term 9, x3 is equal to 1. Now what about the other boxes? So here for the rest of the input combination, output is not defined. So here output is defined for the combination of 0 to 9. What this 4 bit have the 15 combinations, 16 combinations. So out of 10 combinations are defined, 6 combinations are undefined. So for 11, 10 to 15s, we have to substitute that don't care. So 10 don't care, 11 don't care, 12 don't care, 13 don't care, 14 don't care, and 15 don't care. Right? So where we have to put the don't care in the combination which output is not defined for the input combinations. Now we have to make the group of ones. Let us start for this one. And so here it is an 4 variable Karnaugh map. So we have to check first the group of 16. Group of 16 is not possible for this one. Then we have to check the group of 8. So group of 8, one possibility is this. This is not possible because it's include the 0. Another is this. This is also not possible because include 0. So group of 8 is also not possible for this one. Then we have to check the group of 4. So this group of 4 is not possible. This group of 4 is not possible. This group of 4 is not possible. Yes, this group of 4 is. Let me make the group of 4. Right. Then we have to check the remaining ones. This is remaining ones. For the remaining ones, again we have to start the procedure to making the largest group. Means we have to check first the group of 16. So group of 16 is not possible for this one. Group of 8 is also not possible for this one. Then let's make the group of 4. Yes, this group of 4 is possible. Now what about the remaining ones? So remaining ones are 2. So for this one, let's check the group of 16 is possible. No. Group of 8 is possible. Yes. For this one, group of 8 is possible. Right? This is the group of 8 which do not have 0. Right. Now there is no any remaining ones. So not need to do the extra group. Or so in this X3 have the 3 groups, and 3 groups, among 3 groups, 2 groups are the group of 4 and 1 group is the group of 8. So what are the common variable in this group of 4? So common variables are B2, and from the different column it is a B0. So B2 and B0. What are the common variable in this group of 4? So in this group of 4, common variable are B2 again, and from this different column it is a B1. So B2 and B1. What about the common variable in this group of 8? So in the group of 8, only one common variable and it is a B3. So this is the logic of X3. This is the logic of X in a BCD to XS3 converter. Similarly, we have to find out the minimize the Boolean equation of X2, minimize the Boolean equation of X1, and the minimize the Boolean equation of X0. So let me do the process for the X2, X1, and X0. So for the X2, then we have 4 variable Karnaugh map. Right? Here it is an B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar. Here have the B1 bar, B0 bar, B1 bar B0, B1 B0, B1 B0 bar. Let me map from the two table. So for x2, 0, 1, 1, 1, 1, and again 4 times 0, and last is 1. Right? So let me map 0, 1, 1, 1, and 1, and again 4 times 0, and last I have a 1, and rest are don't care. Let me make the group of 1 for this one. So group of 16 is not possible. Group of 8 for this one is not possible. Group of 4 for this one. Let's check this group of 4 is not possible. This group of 4 is not possible. But yes, this group of 4 is possible. 2 from this and 2 from this. Right? So this is group of 4 is possible. Now let me check for this one. Group of 16 is possible, not possible. Group of 8 for this one is not possible. And let me check the group of 4 for this one. Group of 4, yes, this 2 and this 2. Group of 4 is possible. Now remaining is only one ones, so let me check for this one ones. Group of 16 not possible. Group of 8 for this one it's also not possible. Group of 4 for this one it's also not possible. So let me make the group of. So this in x2 have a two groups are group of 4 and one group is group of 2. So for the first group, which is the group of 4, common variable are here it is a B2 bar, B2 bar, and here is B0. So B2 bar and B0. From the another group of 4, B2 bar and the B1. Common variable are B2 bar and B1. And third, the group of 2 common variable are B2 and B1 bar, B0 bar. So this is the simplified the Boolean equation of the x2. Similarly, we have to prepare for the x1. Again a 4 variable Karnaugh map. Right? Here it is, let me substitute. Here it is an B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar, B1 bar, B0 bar, B1 bar, B0, B1, B0, B1, B0 bar. Let's see from the x1, 1, 2, 0, 2, double 1. So 1, 2, 0, and double 1. Let's see if double 0, double 1, double 0, double 1, and last is 0. Last is 0. Okay? And rest of are don't care. So let me check for this one. Group of 16 is possible or not. So group of 16 is not possible. Group of 8. Group of 8 is also not possible. Then group of 4, yes, this group of 4 is possible. Right? Now remaining is this one and this one. So let's check for this one. Group of 16 is not possible. Group of 8 is not possible. Group of 4 is also not possible. Yes, this is group of 4 is possible. Right. Now there is no any remaining ones. So let me write the common variable in each group. So it's in this have the two group and each group size is 4. So from this common variable are B1 and B0 bar. B1 bar, B0 bar. And from this group of 4 common variable are B1 and B0. B1 and B0. Right? So X1 we can say it is nothing but the B1 XNOR with a B0. B1 XNOR with the B0. Now in the last X0 bar. Let's prepare the Karnaugh map for the X0 bar. Here it is an B3 bar, B2 bar, B3 bar, B2, B3, B2, B3, B2 bar. Here have the B1 bar, B0 bar, B1 bar, B0, B1, B0 and B1, B0 bar. So let me check from the two table. So for the X0, 1 0 1 0 1 0 1 0 1 0 patterns. So let us write here in this. First is 1, then 0, then 1, then 0, then 1, then 0, then 1, then 0, then 1, then 0. And rest of our don't care. Rest of our don't. Right? So let me make the group of 1. So for this one, group of 16 is not possible. Let me check the group of 8. So this group of 8 not possible. This group of 8 not possible. Yes, this group 4 from first column and 4 from the last column. It is possible. So one group of 8. Now there is no remaining ones to make the group. So it's only one group. So x of 0, it's only one groups and it is group of 8. So in a group of 8, what are the common variables? So from here the B0 bar and here also B0 bar. So common variable is B0 bar. So x0, it is a B0 bar. So once we'll get the simplified the Boolean equation, next step is to implement all the Boolean equation using the logic circuits. Right? So let me set which variable, which input variable need to be inverted. So B0 is need to be inverted. B1 is also need to be inverted. B2 is also need to be inverted. And yes, so only the three variables are need to be inverted. So how to draw the logic diagram is first is the B3 bar is not required. B2, yes, B2 bar is required. So let me invert it. We will get the B2 bar. Now about the B1, yes, B1 bar is also we need to be inverted. So let's take the one invert kit and invert it. B0 9 and we need to be inverted the B0. Yes, right. Now let's find the x3. So let me check what is the Boolean equation of x3. So it is an ending of the B2 B0, B2 B1 and ORing with a B3. So first is the B2 B0, then B2 B1. So here B2 here and the B0 it is ending and the B2 and the B1 and then B3. So this two ending with ORing with a B3. It produce the X3. Produce the X3. Now what about the X2? So X2 is the B2 bar B0, B2 bar B1. So let's first do the B2 bar. So here it is a B2 bar. So B2 bar B0. So in B1, B0, here it not it B1. Okay. So B2 bar and B0 and another is B2 bar and B1. So here it is B2 bar and here it is B1. And third is B2, B1 bar, B0 bar. So B2, B1 bar and B0 bar. Okay. Pouring of these three terms which produced a x2. It produced the x2. Now for the x1, so for the x1 we can see it is a b1 bar b0 bar plus b1 b0. So it is a b1 bar and b0 bar ending, and b1 and the b0 ending. Scoring it's produced the x1, and for the x0 it is b0 bar. So x0 is a b0 bar, x0, right? So this is the logic diagram of a BCD to access3 code converter. Is it clear? So what is the procedure in any code converter is, first step is we have to prepare the truth table, and from the truth table next step is to minimize each output variable using the Karnaugh map. Third step is to implement or minimize the Boolean equation of output variable using the logic circuit diagram, right? Let's take one more example to a combinational circuit design other than the code converter. You make a practice in your homework for the code converter. Let in your homework that uh, convert convert 84 minus 2 minus 1 to 2421. Convert the code 84 minus 2 minus 1 to the 2421, right? So that you have to do in your homework, right? Now let's take one another combinational circuit design example. So problem statement here is the combinational circuit has four inputs and one outputs. A combinational circuit have the four inputs and one out. A combinational circuit have the four inputs and one outputs. The output is equal to 1 when all inputs are equal to 1. So first condition is output is equal to 1 when all inputs are 1. Second is output is 1 equal to 1 when none of the input are 1. When none inputs are 1 means none of the inputs are 1. And third is output is equal to 1 odd number of when odd number of inputs are ones. When odd number of inputs are, right? So problem statement is design a combinational circuit which have a 4 inputs and 1 outputs. Output is equal to 1 when all the inputs are equal to 1. Output is equal to 1 when none of the inputs are equal to 1. And output is equal to 1 when odd number of inputs are equal to 1, right? So this is the problem statement we have to be designed. So first step is to we have to prepare the truth table as per the problem definitions. So first step 2 we have to prepare its truth table. So in truth table 4 inputs, right? Let's say input 3, input 2, input 1 and input 0. It's have a 4 inputs, right? And it's have a one output. Let's say output is our f. So for the 4 input, what are the possible combination? Possible combination are 16. 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and last is 1, 1, 1, 1. Okay, so it's a 16 possible combinations. So what is our when output is 1? So output is 1 when all the inputs are 1. So output is 1 at the last combinations. And another is output is 1 when none of the inputs are 1. So output is 1 for the first combinations. And output is 1 when the odd number of inputs are 1. Right? So whenever input 1 and input 3 are 1, at that time we have to keep our output is equal to 1. So when both are 1, at which combination both are 1? So here at this it is in 6 and at 7 both are 1. So at 6 and 1 our output is equal to 1. And for again no, here is not. So when odd number, so odd numbers out after the 8 I3 is equal to 1, and so we'll get odd number is here one is 1010. So here output is 1011. Here also output is 1 because I3 is 1 and I1 is also 1. Here also I3 1 and I1 is also 1, and rest is 1110, 1110 and 111 and 111. That's already we have covered in a case of all the inputs are right. So output is 1 for only 4 input combination. One is the all the input are 0. Another is the odd number of inputs are 1. So for such combination are 4. Out of 4, one is overlapping with the when all the inputs are 1. So total 5 times output is 1. And rest of out of 16 for rest of position output f is equal to 0. Now next step is to we have to prepare its Karnaugh map to minimize the output variable Boolean equation or output logic, which require the less number of logic gates. So here the three I2 bar, I3 bar, I2, I3, I2, I3, I2 bar. Here the I1, I0 bar, I1, I1, I0 and I1, I0 bar. So in a min term 0, it is 1 output. In a min term 16, 15 also output is 1 because all the inputs are 1 here. Here all the inputs are 0. Now we have to keep the when odd number of inputs are 1. So odd number is I3. So here all the odd numbers of I3 and I1. So I1 is 1 here. Right. So these are the 1. Okay. Rest of all is 0. . So output is 1 when all the inputs are 0. Output is 1 when all the inputs are 1. And output is 1 when odd numbers of inputs are 1. Means I3 and I1 are uncomplement. So I3 and I1 uncomplement in this group of 4. And so it's group of 4 is. Now let for this one, let me check the group of 16 is not possible, group of 8 is not possible, group of 4 is also not possible. Let me group of 2. Let can check the group of 2 is possible for this group of 2. For that here this one and another we can use this one. Okay. So this have the variable is I3, I2 bar, I1 by I0, and here the variable are I3, I2 bar, I1. So two variable element we cannot make this group. So this is have the single group and have the group of 4. So it's have a two group. One is the group of single. So it's have a, all the variable are present. And another is the group of 4. So I3 and from this I1. I3 and I1. So this is the logic of output. And next step is we have to implement this logic using the logic diagram, using the logic gates. So let's implement F using the logic gates. Okay. So in that let's have the I3 bar, I2 bar, I1 bar and I0 bar. So here is I3, I2, I1 and I0, and it is ending will get a F one of the product term. Another product term it is a I3 and I1. If we pour in these two product term, it produces our output F. So this is the logic diagram of which convert 4 inputs to a 1 outputs, and as per the our logic. So output it will be the one when all the inputs are 0. Output it will be the one when the all the inputs are 1, and output it will be the one when the odd number of inputs are 1. Right? So this way we can design any combinational digital circuit. Hope you have enjoyed and you understand how to design a combinational circuit. Thank you.